Hi students, studying about data and signals. So these are the textbooks that you are aware. This is the fundamental book that we are referring. That's a textbook, Data Communication Networking by Feroza. So these are the previously discussed topics: OSI model, TCP/IP model, the addressing that we have seen, the four different kind of addressing: physical addressing, logical, and then the port addressing, and the specific addressing that is catering to session presentation and application. And these are the topics that we are supposed to discuss today. So now, if we talk about data, so data can be analog or digital. So when we talk about the analog data, what is analog data? It refers to information that is always continuous. Like here, an analogy is given, like of analog data with the clock. We have seen that in our house that we have this clock. So we have got this hour and minute and second hands that gives us information, and it keeps on like moving. So this is continuous forms. The movement of the hands is continuous. On the contrary, when we talk about the digital data, say for example, a digital clock is there, so that is not continuous. Rather, we say it has got a discrete state. Discrete state means at any point of time, if we observe the data, that would be altogether different. So a digital clock, like say for example, right now it is 8:05, so immediately it changes to 8:06. So there is no continuation from 8:05 to 8:06. However, there is a logical reason. Obviously, after 8:05, the time will be 8:06, but this is not continuous. So this is the concept of digital data. So now if we'll try to see the comparison on a graphical way. So you can see that this is a sine wave and this is an analog signal. And you can see these are like the peaks. So this is like continuous form. And if you talk about the digital one, so these are like discrete state. At one point in time, you can see like this complete state. This is like static. Then you have this state, and then you have this state. So it's not continuous like an analog. So this is like the difference. Now more to this digital and analog. Both the digital and analog signals can be periodic as well as non-periodic. So what do you say about periodic ones? Periodic ones are the ones which shows a pattern and in within a particular time frame called a period, and this pattern gets repeated over subsequent identical periods. So the completion of one full pattern is called as a cycle. And if we talk about the non-periodic one, or it is also said as aperiodic, it doesn't exhibit any pattern or cycle. So both the analogs and digital signals can be periodic as well as non-periodic. So the best example of a periodic analog signal is a sine wave. That's a fundamental form. So what is a sine wave? This is a sine wave. This is very simple one. Like in 12th standard, you must have seen that in mathematics, in physics also. Like at the 0 degree, the value is 0. At the 90 degree, this is like perpendicular one. The value is 1. So this is the fundamental form of periodic analog wave. As you can see, the wave starts from here. Oh, let me get it. It starts from here and it goes here in a continuous manner, and it goes here, and here it stops. So this is one one cycle it has completed. So again it will repeat, and this will goes on. This will be like continuing. Now what can you say about like this is more of a sine wave. Here amplitudes are like depicted. So what do you understand by the term amplitude? Like this is the value of the peak. Whenever there is a signal and it is like moving like this, so the maximum value of one particular peak, this is called as the amplitude. So two signals are here. This is one sine wave, another sine wave, and the amplitude values are different. So here we say it's a high peak amplitude, here we say it's a low peak amplitude. Peak amplitude, yes, both are peak amplitude, because there is nothing called as peak amplitude. Amplitude is like the maximum value for that particular thing. So on y-axis it represents the maximum value. So this is the peak value. So now what can you say about the term phase? And like with different amplitudes and frequency, this is one diagram, there is another diagram. So we'll discuss one by one. See, as you can see in this particular example, what is happening is over a period of time, like in 1 second, we are observing that this sine wave starts from here and it completes its cycle here. Now, if you talk about this whole 1 second, what has happened in 1 second is, see, the idea is this curve, this sine wave, it started at this point 0 and it moved here and it moved here and it moved below downwards and it stopped here. Now from here, another like pattern is following and the pattern is almost same. So how many times this pattern is following in 1 second is called as frequency. So as you can calculate, this is like 1, this is 2, this is 3, this is 4. So in all it is 12. So per second, how many cycles are there? So we call it as a frequency. So here it is 12 and the unit is hertz. So we say it is 12 hertz. Now what do you say about the period? Here it is written period, time period is 1 by 12 seconds. So it says for one pattern to get completed, how many like seconds are required? How much time it requires to complete one cycle? So 12 cycles are completed in 1 second. So one cycle will get completed in 1 by 12 seconds. This is the concept of a period. And if you see here, here the frequency is less. So less means it takes more time. As you can see, 1 by 12 and 1 by 6. 1 by 6 is almost double of 1 by 12. So here time is more. However, the frequency is less. So there is one more thing that you can deduce. The frequency and the time period are inversely proportional to each other, or you can say T is inversely proportional to 1 by F, and considering the proportionality constant to be 1, so we can say T is equal to 1 by F. So this is the concept of period and frequency. Period, obviously it is depicting time, so the unit that is used is in the form of seconds. Frequency, we are talking that is 1 by T, its unit is hertz. So it can be hertz, kilohertz, megahertz, gigahertz, terahertz. Now this is one small example, express a period of 100 microseconds in 100 milliseconds in microseconds. So this is simple. The time is given to you in the form of milliseconds. So you first convert it into seconds. So milli is 10 to the power minus 3 and the data given to you is 10 to the power 2. So 10 to the power 2 into 10 to the power minus 3 is 10 to the power minus 1 second. And you have to calculate it in microseconds. So 1 second is equal to 10 to the power 6 microsecond. So 10 to the power minus 1 into 10 to the power 6, answer comes out to 10 to the power 5 microseconds. You can check that. So 1 millisecond is converted into 10 to the power minus 3 seconds, and 1 second is, again it's not 106 microsecond, rather it is 10 to the power 6. So it's in superscript. So we can make the following substitution. Here you can see 100 milliseconds gets converted into first 120 to the power minus 3 seconds, and then if you have to convert this into microseconds, multiply it with 10 to the power 6. So finally here comes the answer, 10 to the power 5 microseconds. Again, one simple question. The power is given to you 60 hertz. Now it is asking you to calculate the period. Already we know this thing. Period is inversely proportional to frequency. Rather, it is the inverse. So time period is 1 by 60. So this comes out to be 0.0166 seconds. 0.016 seconds, it is not that presentable. So what we do is we convert it into milliseconds. Now it is like in a simpler manner, we can say the answer for this question is 16.6 milliseconds. Yes, this is like a good observation. This means that the period of the power for our lights at home is this. See, what is happening is it is saying that at our home, the one cycle gets completed in this time period, 0.0116 seconds or 16.6 milliseconds. And then afterwards, another period gets started, like another cycle gets started. So what it is saying is, then if one cycle gets over in 16.6 millisecond, then why we are not able to see that change? Why we are not able to see that change? Because the only reason is the time period is very small. Like it is, our human eyes are not that sensitive enough to distinguish these rapid changes. So that's the answer for this question. So again, this is very simple. Period is given to you. You have to calculate the frequency. It is 1 by f. So you can do that. Same. This is for your practice. Now, this is one important term. What do you understand by the term phase or phase shift? So phase is something, it describes the relative position of the waveform. Like what I can do is probably let me stop sharing this, and what I'll be doing is I'll be opening up this paint thing, uh, and what I'm doing is I'll be sharing this screen, sharing the screen. Okay. I Yes, I think now you'll be able to see that screen. So what we are doing is, this is like y-axis I have prepared. This is the x-axis I have prepared. And what I am doing is I am making a sine wave. So sine wave is something by default. Sine wave is like this only. This is a proper sine wave. Okay, let me complete with one more cycle, and this is like, yes, this is one sine wave. Now, what is phase is? Phase says generally we have to check any waveform at this position. So this is one position, that is the 0th position. Zero angle is there. So now what I can do is, maybe I can change the phase of this sine form. So if I have to change the sine wave of phase of this sine wave, what I can do is, instead of starting my waveform from this place, I can shift. So when I am shifting this, so I say the phase gets shifted. So this is another sine wave. So there is absolutely no difference. It is exactly similar. Amplitude is same. Maybe you won't be able to differentiate with the help of these two diagrams, but if you'll see, even the frequency is same. The only difference is here, it is not starting from this position. In fact, it is starting from this position. So this is the difference. So this is like the phase concept of phase is. So let me stop sharing this, and again we'll share the our PPT, the usual one that we were starting. Okay, so let me go back to where we were. Okay, so we were in this slide. So this is the concept of, this is like 0 degree. This is like phase shift is there by 90 degree. As you can see, this is what I have explained. There can be one more. This it can start from here also. Instead of here, it has started now from here. So this is a 90-degree phase shift. This is a 180-degree phase shift. Now, what is wavelength? Now, before studying wavelength, let me tell you one thing. Wavelength is something you can relate with the time period, and you can correlate with the frequency also. But there is a small difference between the wavelength and time period and frequency. See, whenever we were studying time period, like we have done in initial slides, we were studying time period and frequency irrespective of the transmission medium. But when it comes to wavelength, wavelength is like kind of dependent on the transmission medium also. So what we can say is, like when we used to be small, maybe in 5th and 6th standard, we used to study one formula: speed is equal to distance upon time. So distance is speed into time. So here we are saying we have got this wavelength, how much it has traveled, the data. So it is equal to propagation speed multiplied by time period. So wavelength is equal to propagation speed into time period, or what we can say, having studied in the previous slides, time period is equal to 1 by f. So we can say wavelength is equal to propagation speed divided by f. So this is the concept of wavelength. Like this is transmission medium at time t. We are observing this. So what can be the transmission medium at time t plus t? So this is the wavelength. Like in time t, capital T, we have traveled this much distance. So we are saying it as a wavelength, and this is the direction of propagation. Now this is one simple application of a simple signal. Probably it's like example given is here of electrical energy that is like being done at our places, houses. So this example you can study. Now, what do you say by composite period signal? See, never very rarely it happens when you are in a practical scenario studying these signals. So the signal is a simple one. Simple one signal is what we have studied. If when we are talking about the composite one, composite says it is a collection of multiple signal, simple signals. So like this is a multiple, this is a composite signal. Here you can see probably you can see here three peaks, like three amplitudes are there. So we can say it is a combination of three single simple signals. So this is like a combination of a composite periodic signal. This is one signal. Now what we are doing is we are studying composite signal one by one. So this can be one signal. Maybe there can be another signal. First we'll study amplitude and frequency. See, this is one signal. So say for example, like in one, it has started here and it has like completed this side. So we can say this is one time. So we can say this, say for example, this is 1 second. So in 1 second, what is happening here is this is like one cycle. Yes, this is one cycle. Then second cycle starts and this completes here, and this is third cycle. So we can say in 1 second we have got three cycles. So frequency is 3. So here we are saying f equals to 3. Directly or indirectly, f is equal to 3 for this value. Now say for example there is one more signal involved here. So we can check here. Now what is happening is amplitude is differing, waveform is more or less the simple, amplitude gets differed, phase is same, frequency is increased, like the speed is now fast, frequency is increased. Now we can see in 1 second, one time frame, it is like cycle is like 1, then you have got 2, now you have got 3, then you have got 4, then you have got 5, then you have got 6, 7, 8 and 9. So what you can say is the frequency here is 9, and earlier you were having frequency 3. So 3 you are saying f. आप लोग क्या कर रहे थे? You were saying कि जो पहले 3 frequency आई थी उसको आप f denote कर रहे थे, and now it is coming 9. So what we can say is the frequency of this blue waveform is 3f. So here it is depicting 3f. Say for example there is one more signal, you have to calculate it, and now we are saying its frequency is 9f. So 9f, like you can check on your own, calculate 1, 2, 3. This will come out to be 27. So this is the example of a multiple signal, composite signal comprising of multiple signals having different frequencies. Now there is one more term which is called as bandwidth. Bandwidth is basically called as the range of frequencies which are contained in a composite signal. So range of frequency means, say for example, in a signal, we have got this the lowest frequency as, say for example, x, and the highest frequency as y. So the difference between the two, we say it as bandwidth. Here in the example it is given, if a composite signal contains frequencies between 1000 and 5000, its bandwidth is 5000 minus 1000, or we can say the bandwidth comes out to be 4000. I believe it is, yes, it is depicted here by the help of diagram. The lowest frequency being the 1000 and the highest frequency being the 5000. So the bandwidth which is available is 4000 hertz. So this you can see. However, it is a non-periodic signal. So this is the example of a bandwidth. Now, needless to say, because bandwidth is the like difference between the lowest and highest frequency, like FH being the highest frequency and FL being the lowest frequency. So we can say the bandwidth is equal to FH minus FL. So now, needless to ask, the unit for bandwidth will also be the hertz only. So here it is an example, like a periodic signal is decomposed into 5 sine waves with frequency of 100, 300, 500, 700, 900. So what is it bandwidth? So it's very simple. 900 minus 100, this comes out to be 800. Now what is here in this question? The bandwidth is 20, the highest frequency is 60. So bandwidth is equals to highest frequency minus lowest frequency. So you have to calculate here lowest frequency. Using that formula, this comes out to be 40. So FH being the highest, FL being the lowest. So this is the formula B equals to FH minus FL. So you can calculate. It's very easily visible. This comes out to be 40 hertz. Now, what about digital signals? See, this is very simple. Whenever we talk about signals, so in majority cases in real world applications, we say that it is the analog signals that is like more evident. Like if I tell you that I am speaking to you, so say for example I am speaking from my mouth, and those signals are getting like transmitted they are getting transmitted by air medium, and obviously air medium is like something analog they are following, and those analog medium analog signals traveled via air that comes to you by your ear, and then finally it is like understood. So this is the story with whole of the communication. It is the analog which is more dominant. But we are talking networking in terms of computer machines, computer systems. So whenever data flows, so ultimately it is the machine that has to understand the data, and that data is always understood by means of digital signals. So in addition to being presented by the analog signal, information can also be represented by a digital signal. For example, 1 can be encoded as a positive voltage and 0 can be as a 0 voltage. This is like very simple. I believe in first year, you must have studied this in maybe electrical or electronics, like +5 highest value, -5 lowest value. So here we represent 1 and 0. So a digital signal can have more than 2 levels. See, when we are saying a digital signal can have more than 2 levels, what is the concept of 2 levels? 2 levels means the kind of input we are having. See, when I am using only 1 bit representation, so like 2 to the power 1 is answer is 2. So I can either have 0 or 1. But when I want to have more than 2 levels, so 2 level means more than 2 inputs I will be able to like forward. So in that case, I have to go with 2 to the power 2. So in that case, like I have to use at a time 2 bits. We'll be seeing this in the subsequent lecture. It is very well written. A digital signal is a composite analog signal with an infinite bandwidth. See, the bandwidth for a digital signal is infinite. However, when you are using this digital signal over some medium, over some transmission medium, so it has to follow the bandwidth of that medium. So in that sense, it is limited. But otherwise, if you talk about a normal digital signal, the bandwidth is infinite. Now this is the example. We want to send 8 bits per second. So for 8 bits per second, what we are doing is we are using 2 levels of information. So level of information means either we have to like transmit in the form of 0 or we can transmit in the form of 1. In the second diagram, probably you can see we are having 4 levels. So 4 level means we are having 4 different types of input. So different types of inputs are 0 0, 0 1, 1 0 and 1 1. So here in 1 second we are able to transmit 16 bits. So is the bit rate 16 bit per second. So this is very simple. We are having 4 levels. 2 to the power 4 is equal 2 to the power 2 is 4 levels. Now this is like very simple question. A digital signal can have 8 level, has 8 levels. How many bits are needed? Now, this is very easy. You want to now have the 8 levels, like in 8 ways, 8 digit 8 different ways you want to represent your data, again by means of 0 and 1. So you can have 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So if you have to represent this, you have to go 2 to the power 3. And otherwise also, like in my representation 0 0 0, I have used combination of 3. So the answer is number of bits per level required are 3. So here is the formula also, log to the base 2, and it is n. N value is here. Now this is even more interesting question. If we have to represent 3.17 bits, see, we cannot do it. Like either we can represent 3 bits or we can represent 4 bits. Like if we'll use 3.17, data will get lost. So we don't want that. So instead we'll go for the representation as 4 bits. So here we'll be having 2 to the power 4 bits, like 16 levels will be there. What is a bit rate? Like it's most digital signals are non-periodic. This we have seen earlier also. Thus period and frequency are not appropriate characteristic, very rightly said. And it is very important to note here also, frequency is generally used for analog signals. So here instead of frequency we'll be using the bit rate. So describe the digital signal, like how many in one time frame, 1 second or one particular unit of time, we can send how many bits. So this is like the expression is, it's BPS. So I believe this is it for today. In this slide, we are having one more portion. So maybe we can see this portion in the next lecture. Thank you.